Hi, I'm Scott Knockleby. In this video, we're going to look at finding the Jacobian for a spatial manipulator. So by the end of this video, you should be able to derive the Jacobian for a spatial manipulator using joint directions and derivatives. So for this example, we're going to use a spatial robot that's going to have a layout of R, parallel P, which is prismatic, perpendicular R, perpendicular R. All right, so here's a schematic of the layout. And in essence, you can see it's a scalar robot that has a pointer group added to it at the end. In this example, we're going to set our tool frame to be equivalent to frame 6, all right, just to make things a little easier. And what we want to find is our Jacobian of our end effector with respect to our base frame 0. So here's our zero displacement diagram for that robot. And using that zero displacement diagram, we can complete our modified D&H parameters as such. And you can see, because frame 6 is equivalent to the tool frame, we just have a row of zeros here. So that homogeneous transform would just be the identity matrix. So we don't actually need to calculate that. So before we can do or find the Jacobian, we need to find the forward displacement solution. So the first step of that is finding the homogeneous transforms. So we have the 6 of them. You just take each row of our D&H parameters and substitute into the homogeneous transform equation. And then for the forward displacement, we just multiply each of those matrices out. And you'll see actually for the Jacobian problem, we actually need the joint directions for each joint, and we get those from each of these transforms. So for joint 2, we'll get it from T02. From joint 3, we'll get it from T03, and so on. So we need to have all of these. So these are the first two. Here's 04, here's 05, and lastly here's 06, which is our full forward displacement solution. Now, to find the Jacobian using joint directions and derivatives, right, we showed that this is the form that our Jacobian takes. Okay, remember, each column of the Jacobian is one joint. All right. And if our ith joint is a revolute joint, our Jacobian takes on this form. It's the partial derivative of our position vector with respect to the joint variable I. That gives us our translational component, and then our angular component is just simply the joint direction. If the jth joint is prismatic, we just need the translational part, which is just from the joint direction, so it's here, and there's no angular component, so it's 0 vector here. So we use this formulation for revolute joints, and we use this formulation for prismatic joints. And recall our position vector x here is just going to be our position from our base frame to our end effector frame in terms of whatever reference frame we're using. Now for this example, we're going to use the base frame to be our reference frame. All right. And so we need our position vector with respect to the base frame. And we're going to get that from our forward displacement solution. All right. There is our position vector of our end effector with respect to the base frame. So let's just highlight that. This is our position vector that we're going to use. Okay, so let's write that out on the next page just so we have it. So our position vector from our base frame to our end effector frame in terms of our base frame is equal to C1L1 plus C12L2 plus C123 S5 L2. That's the x position. We have S1L1 plus S12L2 plus S123 S5 L2 for our x position, sorry, our y position. And then lastly, we have our z position, which is minus C5 L2 minus D4. Okay, and just to make a note, where did we got that from? It came from our forward displacement solution, which in this case is from our homogeneous transform T06. Okay, so now we can start going joint by joint. And so if the ith joint is revolute, we're going to use this formulation. And if the jth joint is prismatic, we're going to use this formulation. All right, so for joint 1, we're going to do the partial derivative of our position vector. So that vector I just wrote on the previous slide. With respect to our joint 1 variable, which is theta 1. So we need to do the partial derivative of this expression here in terms of theta 1. And if you do that, you're going to get minus S1L1 minus S12L2 minus S123 S5L2. We're going to get C1L1 plus C12L2 plus C123 S5L2. And then our last one will be 0 because theta 1, right, if you look at our expression here, theta 1, there's no theta 1 term in there. All right, so that's our partial derivative. And then the other component we need is we need Z1 with respect to our base frame. And now where do we get that? We go back to our homogeneous transforms. Here's T01, okay? And Z1 is this vector here, all right? That's our Z column of our rotation matrix. That's our joint direction. So we'll just draw that or highlight that in blue here. All right, so that is our joint direction for joint 1. So we can write that out and we'll have 0, 0, 1. And we can make a note that we got that from T01. All right, so that's joint 1 done. We can do the same thing for joint 2 now. All right, so we're going to take the partial derivative of our position vector. Now with respect to theta 2, our second joint variable. So we go back to here, we're going to do the partial derivative of this now with respect to theta 2. And if you do that, you're going to get minus S12L2 minus S123 S5L2. You're going to get C12L2 plus C123 S5L2. Again, we'll have 0. We need Z2 now, our joint direction with respect to our base frame. So where we're going to get that, we're going to go to T02 now. So let's jump back to that. There's T02 here, and there is our joint direction. So let's highlight that. All right, and let's go make a note of that on our slide. So it's also 0, 0, 1. Which makes sense because joints 1 and 2 are parallel. So this is from T02 now. All right, so that's joint 1 and 2 done. And we just keep going. So for joint 3, because joint 3 is also revolute, we're going to do the partial derivative of our position vector with respect to theta 3 now. All right, and if you do that, you're going to get minus S123 S5L2. You get C123 S5L2. You get 0. We need joint axis 3 now, so that's going to be Z3 with respect to frame 0. So we need to go to T03 to get that one. Here's T03. Here's our joint direction. Again, it's 0, 0, 1 because these first three joints are all parallel to each other. All right, and so we can go and make a note of that. And again, where we got that one from, that was from T03. So we're halfway there. That's the first three joints done. Joint 4, right, it's prismatic. So all we need is Z4. Terms are our base frame, and you guessed it, we get that from T04. So let's go to T04. There's T04, and you can see there's our joint direction for that one. All right, so we can go write that one down, and you get 0, 0, -1 for our joint direction, and that's from T04. All right, and that's our only prismatic joint. The rest are also revolute joints, so we're going to use the same formula as we did here, except for a different joint. So let's just finish that quickly here. So for joint 5, it's going to be the partial derivative of our position vector with respect to theta 5 now. If you go do that, you're going to get C123 C5L tool. You're going to get S123 C5L tool, and you're going to get S5L tool. We need the Z5 joint direction. We're going to go T05 to get that one. All right, here's T05. There's our Z, our joint direction. Okay, so we can go make a note of that. So Z5 is S123 minus C123 and 0. Again, we got that from T05. All right, and then our final joint is also revolute, so we need to do the partial derivative of our position vector with respect to our end effector point in terms of theta 6. Now if we just jump back and look at our position vector, you can see theta 6 doesn't appear in here. So the partial derivative is just going to be 0. All right, so we have 0, 0, and 0. All right, we still need our joint direction, Z6. We're going to get that from T06. All right, our forward displacement, there's T06. So we need our joint direction, which is that. So we can write that out. We'll have C123 S5. We'll have S123 S5, and we have minus C5. And again, we got that from T06. All right, so we've actually found the whole Jacobian. All right, each of these is a column. All right, we just need to now put it in matrix form. All right, so if you put that all in matrix form, I already wrote it out or typed it out. This is our Jacobian for our robot. All right, it is a 6x6 matrix. All right, because we have 6 joints, and we have so we'll have a column for each joint. All right, column for each joint. Joint 1, joint 2, joint 3, joint 4, which is our prismatic joint, joint 5, and joint 6. And remember, this is the same Jacobian that we use for our velocity problem. So remember, our velocity is just simply our Jacobian times our joint rates. And then for our static force problem, our torques are equal to our Jacobian transpose times our wrench. Okay, so this is the Jacobian we use in our forward velocity and our inverse force. All right, just like we did for the planar case, but how we find the Jacobian is different.